Hello everyone and welcome back to part 4 of the Blueprint Basics series. First, let's check your homework. Building a smooth interpolated rotation logic, just like the up and down movement from the last video. I'm sure everyone did this correctly. Your logic should look similar to this. You should have changed the rotation speed variable from integer to float, created a max speed rotation and an integer speed rotation variable, set them in the rotation input block, and added the same interpolation logic using only the rotation variables to the speed control block. Well done! Today we will start with a new function to get the actual height over ground for our platform. That's a value we can use for several cases. For example, to block the movement of the platform if the height over ground is too low. This way the platform can only start moving at a defined altitude. Or we can change other things at a certain height, like sound or light effects. And we cannot use the Z location of the platform in terrains with different heights or obstacles. So we need a way to measure the distance between our hovercraft and any object underneath. To do that, we can send a ray straight down from our platform until it hits something underneath. There is a node that does exactly that. Right-click and search for Line Trace. There are a couple of options, but for our use case, we choose Line Trace by Channel. The channel value is set to visibility by default. That means the trace will generate a hit on everything that is visible in our scene. Exactly what we want. Start is the starting point of our trace ray. That should be the world location of our platform. So add a get world location node to that pin. End is the end point of the trace. If we want to trace straight downward, X and Y stay at the actual platform location and only Z needs to be lowered by the length of the trace. So add another getWorld location node, just to keep everything clean, and split the output vector. Also split the end vector input of the trace node. Keep X and Y unchanged, and for Z, insert a subtract node. Because we want to trace down, we need a negative value. Let's say 1000. More than enough for now. If you want to see the trace in the viewport, you can enable Draw Debug type. Set it to for duration or persistent, and the engine will draw a line from the start to the end location. That makes it much easier to understand what the trace is hitting and helps you debug the height calculation. Okay, now right-click the out hit pin and split it. Now we've got a ton of outputs, and one of them is exactly what we need. The distance between the start point and the hit. Create a new variable, name it height over ground, and store the on-hit distance value in it. The trace now hits anything that's up to 1000 units under the platform. But what if the altitude is higher than 1000? Then the trace will not hit anymore, and the distance value is 0. So we need to check if there is a hit or not before setting our height over ground variable. The return value pin gives us this information. True means hit, false means no hit. Add a branch to that pin. If there is a hit, set the variable to the on-hit distance. If there is no hit, we know the altitude is at least 1000, then set it to 1000. To execute this, create another custom event. Name it height over ground and connect the execution pins. Now we can call this new event from the end of the platform rotation block. And we can use our new variable directly to limit the rotation functionality until the platform reaches a defined altitude. Bring in our new variable. Compare it, for example, if it is less than 50, add a branch, and only if it is not less than 50, set the rotation. Connect the custom event to the branch and the true pin of the branch to the height over ground call. Compile and test if it's working. Now our hovercraft can only rotate if the altitude is higher than 50. Okay, now we'll finally add the forward movement, so we can fly around all over the level. That works a little bit different than the rotation or the up and down logic, because we don't want 4 keyboard inputs for forward, backward, right and left. We want the platform to always move to the front, depending on the rotation angle. If we want the hovercraft to move forward, we first need to know what forward actually means. Think of your hovercraft like an arrow. Wherever it is in the world, the arrow always points in a certain direction. And that direction changes whenever you rotate the craft. Unreal takes the rotation and turns it into a unit direction. This is what we call the forward vector. Instead of us doing any math to figure out where x and y should point when we rotate, we just ask the engine for the forward vector. Let's set that up. Get the world rotation of the platform. Then get the forward vector from the rotation simply by adding a get forward vector node. To move forward, we simply multiply the forward vector by our speed. Create a new float variable for the forward speed and multiply it with the result of the forward vector node. Then simply add this new vector to our current location. So get the world location of the platform and add it to the result of the multiply node. And set the result back to the platform's world location. Wherever the hovercraft is looking, that's where it goes. To execute this block, create a new custom event, name it forward movement and connect it to the execution pin. To keep collision detection on while moving forward, enable sweep. Call this event at the end of the height over ground block. To set the forward speed, we need to expand our input section as well as the speed control block. You know how it works. Create the max and integer speed variables and add a keyboard or gamepad input and expand the speed control setup with the forward variables. Alright, now we can finally fly around in our level. Try to implement the height over ground comparison to the forward block as well, to make sure the platform moves only if the altitude is greater than 50. But this series is not finished yet. There are more things to come, like random hovering rotation, engine light and sound effects, camera control and more. So stay tuned for the next part. Cheers!